Coming to our seminar for the Center for Robotics and Biosystems. I'm very pleased today to introduce our speaker, Mark Yim. Mark is the director of the Grasp Lab at Penn, which has been around forever. I remember when I was looking at grad schools, I remember the Grasp Lab, and I see from the website that it was established in 1980. So one of the oldest continuously operating sort of centers for robotics in the country. So I've known Mark and his work for a long time, and what's really exciting about Mark's work is how innovative the electromechanical designs are. So he and his groups build a lot of really cool different kinds of robots, and they're actually working with Mike Rubenstein and Bill Strong and others here at Northwestern right now, and on some interesting stuff too that we might get to see later. So a really innovative electromechanical designer. Let's see, what else can I say about him? Mark is an editor of the IEEE Transactions Robotics, which is a very important job. He is a holder of more than 50 patents. He's a member of the National Academy of Inventors, and just an all-around great guy. So thanks, Mark, very much for coming today and giving us a talk, and I will turn it over to you.
Great. Thanks, Kevin. Actually, before we get started, I was thinking of making this somewhat informal. I kind of like the opportunity. I really appreciate the opportunity to present because, presentations are very different than papers. Like presentations aren't peer reviewed. I can like throw stuff out there and say things that are maybe not true and see what you guys say in response to that. Or, it's a little bit more interesting. So thanks for this opportunity. One thing I do want to do is get a little bit of an idea about you. If you could like give a thumbs up if you are a grad student, in the reaction thing, just to let me see roughly how many grad students. And okay, great. How many undergrads? Are there any undergrads? Some? All right, great. Okay, good. So I guess I will, some of this, I like to sometimes give, advice to PhD students who are thinking about research or that type of thing. So one of the things that I will be talking about is impact. And, what do we do as researchers? Why are we doing what we do? And almost always it's for impact. How can we make the biggest impact on the world? We don't become professors for the money. So that's kind of where some of this is coming from. When I talk about is cost-effective robotics interesting, the focus is also on impact. But before we get into that, I want to talk a little bit more about the Grasp Lab, since as Kevin mentioned, I am the director. I feel it's kind of like my job also to tell people about the Grasp Lab. It is 41 years old now. Actually, I should update this. And despite what some other people at like particular other university in Pennsylvania say, we are the oldest robotics research lab in the country. We've got about 19 faculty in all kinds of areas, which is really great. The way that we can interact doing interdisciplinary things is really wonderful. I think you guys have also started to do that, which looks really great as well. Okay, so that's about the Grasp Lab. Why do we need to have cost-effective robots? Why do we want to have low-cost robots? If we look at what people have done so far, researchers with robots, it's pretty impressive. Like this is the picture of the PR2 from Willow Garage, and over the past decade or so, we've seen demonstrations of autonomous towel folding, baking cookies, putting dishes away, all these other different types of tasks. The towel folding one was a pretty impressive, machine vision and understanding soft materials, all that kind of stuff. It got some press because the senators and the government were saying, why are we having robots fold towels? Because it takes like 15 minutes to fold one towel, and it's not even necessarily done very well. and that they actually have a good question. Part of the thing is that the robot costs $400,000. Who wants a $400,000 robot to do a bad job? It's just not useful. It might be useful to have folded towels, but not if it costs $400,000. Baking cookies, the examples, they show these example of baking cookies, and there's like flour all over the place after they've baked it. It's the robots can do these things, they're just not good at it. So if we can lower the cost, at least maybe it might be worthwhile. Another example robot, this is a system from Mark Miskin, who's a new professor at Penn who did this work at Cornell. So this is maybe the lowest cost robot. They would make like 100,000 of these at a time in silicon. And so because they're making so many in this one process, they can be really cheap, like a couple pennies. And in this particular case, by shining a laser light on two different spots, you can get the robots to kind of walk. But so it's pennies, it's super cheap, but what does it do? It kind of walks. It doesn't actually do anything useful either. So this is like the other spectrum from the Willow Garage robot, the PR2. Ultimately, you want to ask, is it cost effective? Means it doesn't only have to be low cost, but it has to do something that has value. And so ultimately, that's what we want to look at. How do we have impact? How do we make impact on the world by making robots that do something useful that people might actually want? And this is where, I get to the thing which I put in my abstract. When you talk to other engineers, they always talk about the science they're doing, and often low cost aspects of anything you do in engineering or science doesn't get a lot of respect. And because it's just engineering, you just engineer it and then it'll be low cost. We've done all the hard work by coming up with this whatever scientific thing, and then you just do the scut work to make it low cost. That's one of the things that I kind of rail against. But so the typical example process of doing things is you start with the prototype of some device that does something important, and then you cost reduce that by doing something like design for manufacturability. Everybody talks about just come up with injection molded and plastic, it'll become really cheap. Use economies of scale, you exploit some type of standardization, you apply processes to make things cheaper. And this is why it doesn't get a lot of respect. And in general, when we talk about cost effectiveness or low cost, it's always compared to something else. And if you start with a prototype, it's easy to, you have that thing that you're comparing it with, so you can cost reduce and everything makes sense. If you don't already have that prototype, what are you comparing with? And so what I'm proposing is not doing these types of things for doing cost-effective robotics, but rather, can we, instead of starting with a design, can we look at a function, a target function, and develop a low-cost design for that function? And what are some of the principles towards that process? So that's basically what this talk is going to be about. And so these are a couple of the principles that I'm thinking would apply to most of the things I talk about. There are essentially, you can trade off complexity to make things lower cost as you try to get to a certain target, or look at the thing that you want to do, and do you really need to have all those requirements, or can you, remove unnecessary things that don't actually contribute to what you really want to have happen. So within the complexity for trade-offs, there are a variety of things you can do, like trade off complex mechanisms for computation, find expensive computation and replace that with some passive mechanism, or reuse certain resources through time multiplexing, or something I call removing parametric cost differentiators. So I'll get into a little bit more examples of these things as we go. So this slide you'll see again and again as I talk about these different aspects. Okay, so let's jump into an example. Any robot will have motors in them. Actually, I want to try something also in chat, if you guys can. If for anyone who has made a robot, can you just say me in chat, just so I can see how many people have roughly. All right, so there's plenty of people. All right, so there's maybe 20, 30, somewhere between 20 and 30. All right, and of those, how many of you have in your robot used a Maxon motor? Okay, so it looks like probably half, maybe more. So Maxon motors are very popular. They are also very expensive. So one of the things that we were looking at, this actually is a funny story. If we have time at the, I don't think I have time, but if we have time at the end, I'll tell you about my dealings with Maxon, which actually incentivized me to come up with a way to come up with a different approach. Can we come up with a way of using cheaper motors than Maxon? And why is it that everyone uses Maxon motors? So to a large extent, from what I know from most people, it's because you want to have smooth motors. You want to get rid of the torque ripple. If you take a motor and you kind of twist it, you can feel the bumps as just from the mechanism inside. And we'll talk a little bit more about that. So this table shows a chart of price versus this, what we call torque ripple ratio. These are all motors that are about the same size and roughly the same torque capability. If you take that torque ripple, the amount of peak to peak variance, and divide it by the maximum torque, and then plot that versus its price, you get this graph, and it's somewhat, not linear, but you can kind of see a curve there. This guy, the most expensive one, is a Maxon motor. These guys are hobby motors. So this previous picture, this is a typical outrunner, which has a large torque, but as you get to cheaper and cheaper motors, which have larger and larger torque, they also have larger torque ripple ratio. And it's actually fairly consistent along these lines. So the goal here was to see, can we actually come up with a way to use these lower cost motors and somehow get rid of that torque ripple? And why is this important for robotics? If you've done anything with haptics, you can feel that ripple, and that's a problem. If you do want to do something like just make a path, this is a square with the cogging removed, and if you saw that green path, it's kind of wobbly. So it's kind of useful to have a way to get rid of that ripple. So where does torque ripple come from? There's two main sources. One of the things is you've got this, for outrunners, you've got the rotor on the outside with the magnets and the stator, which has the coils on the inside. Very often people use what they call sinusoidal commutation to reduce that torque ripple, but it doesn't do everything. It's usually not perfect. It's going to be slightly off. And there's so that's from the mutual reluctance torque. But there's also this cogging torque, which just comes from the magnets being attracted to the stator. And that you can't get rid of, through any type of sinusoidal commutation. You have to know what it is. So there are ways of other approaches for getting rid of or reducing this torque ripple ratio. And that includes, the different types of commutation, which doesn't do everything. People have put torque sensors on the motors and then closed loop feedback to reduce it. Is a very expensive way to do it. And then there's the Maxon method, which is they have this expensive basket wound coils. And the way they do it is proprietary or whatever, but it makes it very expensive, and it has very low torque ripple ratio because of it. There are other kind of experimental ways of doing things like skewing the stator and other kinds of interesting things, but they're typically very expensive. So what my student, Matt Piccoli, came up with was a way of measuring this torque ripple ratio by putting a position sensor on the motor. And if you have a robot, you're going to have a position sensor on it anyway. So once you have that position sensor, you can use these. There's two different approaches. You can either add an increasing amount of current until it just starts to move to find out what that torque ripple is, or you can do a constant torque and see how the speed varies. And essentially you can map out that torque based on the different position. Once you have that, you can invert it and then apply this to every command to compensate for, depending on what the position is, to smooth out what the motor looks like. So how does it work? This is that graph I showed you before. The green circles are the torque ripple ratio with the anti-cogging turned on through this method, which essentially we got for free because the sensor is already there for robotic applications. The thing to note here is this guy, this cheapest motor down here, is better than the Maxon motor. So the cheapest motor, which is the Maxon, is 9.4 times more expensive, almost an order of magnitude more expensive, but it performs better. It's smaller, it has higher torque, all around, and all of them actually perform better than the Maxon motor. Matt has now started a company called IQ Control now. I think it used to be called iKinetic, IQ Motors. If you want to buy one of these motors, it's they're actually pretty good. So that's one way of doing things. So essentially, this is what I call the parametric cost differentiator. The torque ripple ratio is a parameter, and it's a differentiator which makes the cost different. So if you can remove that, you can then get more cost-effective results. There's a question in the chat: what kind of encoder resolution is required? This was, I think, this was one of the Austria Microsystems magnetic encoders, and it was like 1,000 or 2,000 resolution or something like that. I'm not sure that you need that, but those are cheap and they work well. So compared to Maxon motors, we were able to remove improve the torque ripple performance. There's another thing that's interesting here. So we utilized a cheaper motor. I wrote a proposal with Alison Okamura, who I think many of you know, and she has this thing that she says, anytime you see the word utilized, don't use it. Use the word use, because in this particular case, use is more cost effective than utilized. It's shorter, it means exactly the same thing. So you don't ever need to use the word utilize. So in my parlance, it's more cost effective. Okay, so the rest of the talk, I'm going to talk about examples of tasks. And the tasks robotic tasks can be broken up into two, manipulation tasks and locomotion tasks. First I'll talk a bit about positioning and grasping examples, and then an example of land, sea, and air, different robots. Another question in chat: since Maxon motors are proprietary tech, is it possible it is a cost-effective method, but they're just selling it at a much higher price? Yes, that's possible. Who knows? Okay, so when we think about and we want to compare tasks with the cost of a task versus the value of a task, and what are we going to compare it to? Well, a question we often think about when we think about target tasks is, what do humans do? So in manipulation, here's a picture of a person sitting at a desk. Very often, you'll have different things like a telephone or whatever that you have a desk, and you might want to manipulate them. Let's say you wanted to manipulate that lamp. How many degrees of freedom would you require? Usually when we design robot systems, the costs are driven by the number of actuators, and the number of actuators are usually somehow correlated to the number of degrees of freedom. So if you have a normal arm, might have 6 degrees of freedom, 6 motors, and one of the things, if you have 6 degrees of freedom, let's say you wanted to adjust the lamp, there's this thing that, the elbow down or elbow up configuration issue, because the inverse kinematic solutions that have multiple solutions. And in this case, this elbow may be bumping into the table, or in the other configuration, maybe bump into the person. So a lot of times what people do is they'll add a 7th degree of freedom so you can adjust that elbow to be wherever you want. So you might end up with like 7 motors. One of the things that you might think about also with a robot arm is the reach. How far does it need to go in order to for the workspace to satisfy the task that you have? So again, if we look at a different parameter situation, this graph is, here we've got the x-axis being the reach, the arm reach, and a bunch of different industrial robot arms plotted out. And these are all 6 or 7 degree of freedom robot arms. And the cost is the vertical axis. So again, in this particular case, the line is pretty close to quadratic. So it's the cost goes by the reach squared. So, a lot of times it's useful to think, does that make sense? Why would it be squared? If we analyze a robot where we've got, certain reach, scale, L, and a given force that you might want the robot to apply at the end effector, again, usually we think about looking at the motors and transmission, as that's usually where the dominant part of the cost comes from. Motor and transmissions are usually linear with power, torque times speed. For a given speed and payload, then the cost will be relatively, proportional to the torque. If we double the size, double the reach, what happens for the same amount of force? Couple ways to think about it. If this design has an elbow and we put a motor out at the elbow and the motor has mass, if it needed to have more torque because now the part of the arm is larger, then it would need to be bigger, and that mass would then increase the requirement of the torque at the shoulder. And so, so if you do everything proportionally, basically it goes by the L squared. Or if the weight of the arm itself is going up, then that you also have to compensate for that. And so that's another reason why it might, the combination of that with the motor mass or whatever, basically you can see that it'll be super linear and possibly quadratic. So it kind of makes sense. So one of the things that I think is that I've been thinking lately that elbows are bad as a general rule for manipulator arms. I don't know if it's true, but so how can we get rid of elbows? There's a really old robot arm configuration called spherical robots. These are polar robots. There's a prismatic joint in which this thing goes in and out. And in fact, the Stanford arm, the very first industrial robot arm, was this, and as well as the Univ, they had this configuration where the one joint is prismatic, and then it's more on like a shoulder that can go a 2 degree of freedom shoulder. Okay, so there are configurations in which there is no elbow. I want to do another thing in chat. I want you to look at these pictures and tell me in chat, what are they doing besides doing something with their arms and hands? What do you see that these people are doing? Yeah, they're looking. What are they looking at? They're looking at their end effector, that the thing they're manipulating, right? They're looking at their hands, right? They can see what they are doing with their hands. And so this is kind of an interesting insight, right? If you can see what they're doing. And actually another thing, if you think about the way we design offices or our workspaces, like you might have all of these different things around your desk and you can reach them, but you can also see them. You can see the things that you want. So there is a line of sight between your eyes and whatever it is that you want to manipulate. If you have that line of sight, that means that it's obstacle free. Obstacle free means that if you had a robot arm, attached to your head that went out to the objects, you wouldn't have to worry about doing any collision motion planning or collision detection, because the path is there because you can see it. So that's like one of the things that you get for free if you had no elbow. So one of the things we were thinking about is, okay, can we come up with a design that has no elbow, or come up with a nice prismatic joint? One of the reasons that I think the old Stanford arm and the Unimate arm didn't do so well is because the prismatic joint is expensive. And not only is it expensive, it's usually like a rack and pinion. One of them was a rack and pinion. You have this big bar that the backside, when you try to retract it, the backside, it sticks out the backside, and that causes a problem because then you have this problem of collision on the backside. If instead you had a prismatic joint that could expand or collapse more easily with a large expansion ratio, then you might be able to come up with something useful. So we came up with this thing we call the spiral zipper. Actually, there are related products that are already out there that are something like that. And you put it on like a gimbal with cables at the end, then you can have essentially a positioning device, a 3 degree of freedom positioning device that has no elbow, that could be really useful. Besides having a large reach, that the reach doesn't scale quadratically because the mass of the arm doesn't grow. The majority of the mass is in the base. The tube is actually very light. And in fact, because it's a tube, it's essentially optimal in strength to compression strength ratio, length to strength to weight ratio for under compression, having a tube shape. The other thing is, so that means that the cost scales linearly with reach. As the reach gets larger, the forces at the base scale linearly with how far it goes out, not quadratically. So again, this is removing the parametric cost differentiator, and then we get this collision avoidance thing for free, which is kind of nice. So that's a positioning example. Grasping, what we don't have is grasping out at the end. We still need a gripper at the end, and of course we might also need orientation. If you look at grippers, there are these high dexterity hands that I would say is the opposite of low cost, and I might also say the opposite of utility. Some of them cost like over $100,000 with like 20 actuated degrees of freedom. Do you really need all that? What do you need that for? The trend in the industry, I went to one of these ICRA trade shows a couple years ago, and there were like 3 robot companies that were selling under actuated hands. So these things are the ones which have cables typically, or different type of transmissions, in which there's one motor that drives the fingers or the hands, and because of the cables or the way that they do the transmission on the inside, it'll automatically wrap around objects, or a parallel jaw type gripping, a slightly more improved version. This is a picture of the Velo 2 that Matteo Carli developed while he was at Willow Garage. So that's a trend and an example of moving in this direction of reducing the number of degrees of freedom to get lower cost and still have high performance. The thing that I was thinking about is, what about 0 motors? What's better than 1 motor in terms of cost? 0 motors. So what can we do with 0 motors? So the idea here is, if you think about objects, this probably won't work for every object, but there are a class of objects in which you can pick them up without having to close on them and apply opposing forces. So this is a way to pick up objects statically stably with a 0 degree of freedom gripper. First, you'll notice it kind of flips back and forth as it tips it one way, and then it has to flip the other way in order to grab it. And if the center of mass is offset from where it's picking up, then you can grab it stably. We've also developed a little a way in which there's a kind of a force sensor on the inside, and there are different states in the tilting and picking up position in which you want to, you can sense with that force sensor, both for picking up and putting down, which is pretty straightforward. Another thing that's kind of more recent, so this is a paper that hasn't come out yet, but instead of having to do things quasi-statically, what if we could kind of accelerate the arm and pick it up really quickly? And so if you do it wrong, if you don't accelerate in the right way, then the object slips out of the grasp. If you do it almost right, sometimes you can get it to stay, but it slides a little to the end. And here's one where it actually, if you scoop it up so that, and rotate it in the right way, you can actually pick it up without having to grasp it. And this actually uses, this is all based on stuff that Kevin Lynch and others have done in terms of analyzing forces as you try to manipulate objects. So there's the center of mass, the contact points and the locations of those contact points, the friction cones on the cylindrical object. And then in this case, we also add the inertial forces as you, along the path of grasping it, and you can guarantee that it has stability as you lift. So how well does it work? We did something like 150 trials, and it was about 95% success rate over different objects. This is with just modeling a cylinder, but including objects that have liquid that change its mass or other things that we didn't actually model. It still has worked fairly well for most of these cases. The other thing that's kind of useful is, I don't know if you've seen demonstrations of robots handing an object to another person. A lot of times it's really awkward because the robot doesn't necessarily know exactly when to let go. And so the person grabs the object and has to kind of yank it out of the robot's hand. And then until the robot senses, oh, he's trying to pull it out, and then they let go. But if you don't have a gripper that's grabbing onto it, transferring the object is easy, right? The person just takes it out, which is kind of nice. So in this particular case, the principle that we're using is that, for certain objects, there are ways that we can use these, we can remove these extra degrees of freedom because they aren't necessary for these objects. In this particular case, the objects have to also have, be kind of long so that we can get the stability from the center of mass being offset from where we're grabbing it. All right, so those were some manipulation examples. Let's look at some mobility or locomotion examples. For flyers, in particular, let's look at a helicopter. A helicopter has this thing that's called a Swashplate. So in the Swashplate, it's actually a very complex mechanism. It has 5 linkages, 8 ball and socket joints, a ball bearing, and 2 servos. So there are essentially 3 actuators. There's the main rotor that spins this thing, and then 2 little servos that change the pitch of the blade as it spins around in order to get attitude control. So the Swashplate provides this attitude control. So my other student, Jimmy Paulus, came up with this idea of kind of modifying the blades. Essentially, if you look at a normal helicopter blade, they will very often have, not all of them, but many of them have this, what they call a lead lag hinge. So these hinges are vertical and allow the blades to swing backwards or forwards. Normally, what a helicopter blade will also do, they'll change the pitch. As the blade is spinning around, you may increase the pitch or decrease the pitch by rotating about this pitch axis. So the idea that Jimmy came up with was to change the angle of the lead lag hinge. If you angled it, then what would happen is if the blade leaded or lagged, then you would also get a pitch change. So this is actually what the mechanism kind of looks like. You can see that the lead lag hinge is not vertical, it's actually at an angle. So let me, it might be easier to show you just by, pretend my arm is the blade. So this is lead lag is rotating about the shoulder. This would be lag, this would be lead. By changing this axis from, instead of being vertical, it's now at an angle, that means the blade does this. So if it went to lag, the blade would go down, and as it went down, the pitch would change. So if changing this way would increase the lift. If you have a pitch like this, that increases the lift. If you had a pitch like that, that would decrease the lift. So the idea here is if using the main rotor, if you suddenly pulse the motor so that the blade would lag, that would also increase the pitch. And so you get pitch control by varying the inertia of varying the, pulsing the main rotor without having to add extra servos in the Swashplate. So essentially, we've got rid of the whole Swashplate, all the mechanism, 2 servos, and we're just using the main rotor to pulse to get pitch control. So this is what the system looks like, and does it work? Yeah, it does. Here you can see it. It works pretty much. You can do everything that a quad rotor can do. It is under actuated. It only has, in this particular case, there's 2 motors instead of 4. So the way we do that is because it's spinning so fast, you have to wait for the blade to be in the right place before you pulse it. And so essentially we're doing this thing that I call time multiplexing the resource. So we are time multiplexing to get that one motor to act with that mechanism as if it was the 4 motors that you have on a quad rotor. So it's a much simpler structure. And one of the main advantages of this thing is that without all of those linkages and ball joints, it's much more robust. Usually in helicopters, the Swashplate is one of the things that the maintenance people have to worry the most about because it is so complex and it's critical to the function of the helicopter. If something happens, it's a bad thing. So without all that thing there, it's much more robust. All right, here's another question for chat. Is this vehicle holonomic? And so by holonomic, I mean you place a frame onto this part of the vehicle. Are there no non-holonomic constraints on the control? Can we instantaneously move this in any direction, any of the 3 degrees of freedom? So just a couple people willing to take the leap. So if you haven't seen this vehicle, this is it's got mechanism wheels, and yeah, this is a classic example of a holonomic vehicle. You can rotate these things and it can go sideways because they have these wheels that are allowed to spin rather than move normal. So this is a classic example. For those of you who have not seen this before, classic example of a holonomic vehicle. So holonomic vehicles are usually made up of these things called omni-wheels or mechanism wheels. One of the properties of these things is that they are relatively expensive compared to the amount of load that they can have. And not only that, you might think about what is the size of an obstacle that a wheel can cross over. Usually it's some like 1/4 to 1/2 of the wheel diameter. But for these things, it's not this wheel that's important, it's this wheel diameter that's important. So these guys can barely cross over these tiny little bumps. Like if you had a power cord lying across the floor, they may get stuck because it's using these tiny little wheels. Nobody has, cars with tiny little wheels because they get stuck on small things. So the performance is not very good. They only really go on very flat terrain and they're expensive. All right, here's another question. We have a diff-drive robot. Diff-drive means there's 2 powered wheels in the back and casters in the front. We attach a frame to the front, to the top. Is this vehicle holonomic? Should, follow your department chair's lead. Right. This, of course, this is not holonomic. It only has 2 motors. There's no possible way that it can do 3 degrees of freedom with just 2 motors. But what if we attached a turret on the top of this diff drive with the center here and added this 1 degree of freedom? So now we've got 3 motors in this configuration. Is this holonomic? It's a little bit more difficult of a question. on no. Can't go sideways. So what does it mean to go sideways? We've attached a frame, and can this frame move sideways? Actually, you can. Right. So in this case, this vehicle is holonomic. So this is a thing that I get so many people look at this and they see diff-drive and they say, not holonomic, can't be holonomic. If you put, it depends on your frame of reference. If you put a frame here attached to the center of rotation for a turret that also spins, this is holonomic. A critical thing here also that often people don't realize is if you have the axis of center of rotation for turning the two wheels, if that's offset from the turret, it will be holonomic. If it is not, if you align the two, it won't be holonomic. So here's just as proof. It's a vehicle that we call HAMR. I forgot what it stands for, but you know, you can do all the things. It can instantaneously move sideways. You can do different motions. The other nice thing is that it can go over large bumps because it doesn't have those tiny little omni-wheels that cause problems. In fact, this particular vehicle can go over any type of OSHA standard, not OSHA standard, what is the American Disabilities Act, ADA compliant house. You know, there's certain rules about the size of bumps that you can have in the floor. This vehicle can go through all of them, which is kind of nice. So how do we know that it's holonomic? We can look at the Jacobian. So here's the Jacobian for this vehicle based on this where the wheels are placed. This B is important because it comes out in the Jacobian. If we have the wheels aligned with the center, so a typical thing when people design robots, you know, you want to have some type of symmetry. It's nice to have these two wheels, driven wheels here. You put two casters in the front, caster in the back. This is very common. In fact, if you think about the most common robot in the world right now, it's probably the Kiva systems, the Amazon robots. They've got, you know, hundreds of thousands of them, and it may be the single most common robot in the world because there are so many of them. They are all designed this way. They have driven wheels and two casters on either side. If you write the Jacobian for this guy, this is Jacobian for that. What's wrong with this matrix? Does anyone see anything wrong with this matrix? This particular Jacobian? You can type it in chat. Degenerate or singular. This is a singular matrix, right? This row is a linear combination of this row. It's singular. This particular configuration is singular. It's in a singularity. This is why it's not holonomic. And people often think of that when you put a turret on there. If you have a turret that's aligned with the center of the wheels, it will not be holonomic. All right, so you know, we wrote a paper on this. It turns out that this idea is over 2 decades old. Leslie Cabling wrote a paper on this in 2002. Why? The thing that gets me is, why is anyone using mechanism wheels? Why is anyone using omni-wheels? Because this is just better. There may be a situation in which it works because you don't want a turret in this particular configuration. But, you know, you need 3-4 motors for those things anyway. It just seems like this is just so much better. It's cheaper. You don't have the problems of going over things. Has a higher load capability. Anyway, so it's basically, you know, so we're trading off the complexity. Why are the mechanism or omni wheels more expensive? They have a lot of little tiny wheels with a lot of little tiny bearings. We do need a slip ring. If you need, you probably need a slip ring. If you know, sometimes you don't necessarily care about winding up, but yeah, you might need a slip ring, which sometimes can be expensive. Okay, that's a good point. All right, on to another example. How am I doing on time? Am I?
I think nominally we have 3 to 5 minutes left before questions.
Okay.
Do you
Uh,
need much more than that? we're
I've
gonna we're gonna we're gonna wrap around 1 hour, so right around 14 minutes from now we're gonna wrap. But then people like me who want to hang around and just talk more can hang around.
okay. All right. So I'll speed up a little bit. I think I'll go over a little, uh, but I'll speed up a bit. Um, so another flyer. This is a if you you can get this thing from Amazon for $20, and they say they're the smallest quad rotor in the world. Uh, we took it apart and looked at all the different pieces, and the most expensive single component was the IMU. So it has an IMU on it, and one of the things the IMU is used for is for stability. You know, active stability. It's what the CPU uses to keep the thing from falling over. This is what instability looks like. So this has no IMU. It's essentially things go unstable. They kind of spiral around. We're just trying to get things to fly up, but it keeps going sideways and then falls down. So that's essentially instability in a flyer. One way to get rid of instability passively is to put drag plates on. Essentially, this is a system that has the IMU removed, and instead you put these drag plates, which basically, when the thing starts to slip sideways, you put some drag plates that will cause it to upright itself as it moves sideways. So if it starts to go this way, it tilts the vehicle the other way, so it stops going in that right direction. And so this is, it works pretty well. So here's another kind of interesting thing. If you have this is called a Chinese top. It's basically a propeller on a stick. If you spin it, it's passively stable in the sense that it starts out at an angle, you spin it, and it self-rights so that it goes continuously right. This is another example. Here's this Chinese top, but it's upside down. We're going to spin it the same direction, but the stick is going to be on top. So intuitively, you might think, using the same mechanism from before, the center of pressure over the center of mass would cause it to go the right way. This way would be unstable. But what happens is it's actually stable. So if you walk this in slow motion, it starts off at an angle, but as it spins, it rights itself. Despite the center of mass being above the prop, which would be the center of pressure, it self-rights. So why does that happen? It's essentially it's because of differential lift, which I don't have time to go into. But basically, there's another thing that causes things to work more passively. And if you make a vehicle that's flat, and make sure that the lifting components have the most mass, then it will be passively stable. So you can get rid of the IMU and make a passively stable mechanism. So what we did was we realized you can do that. If you take a motor, two propellers, and put them together, you can make this. There's just nothing. It's a super simple robot. It's just a motor and two propellers, but they have to be made in a way that it's passively stable, so you don't have to have all this extra mechanism to make it fly correctly. So this gray part that has the batteries on the outside has the most mass and has lifting surfaces, and so it ends up being passively stable, and also it's in the Guinness Book of World Records for being the smallest flying vehicle. Mike Rubenstein and I later got a DARPA contract to see if we can make it even smaller. We ended up making one that's smaller than 2 centimeters, and that, we didn't submit that, but it is now. We do have the smallest vehicle in the world record. More recently, this is actually, I think, from a couple days ago. Mike and Bill Strong and Drew Curtis, I don't know if I spelled that right, have also made this vehicle be controllable. So building on what we did with Piccolissimo, a key to this is that the motor needs to be, and the spinning axis of the propeller needs to be offset from the center of mass. If it's offset, then you can get these, you can do control, 3 degrees of freedom. You can have to, step response or follow a path or do whatever you want. These guys did some fantastic work in actually getting this to work really well. So by having it offset, you can kind of pulse the motor at the right time, and that will get it to change its attitude. Another kind of funny thing about this is that all of the complexity of the system is in this the frame, where we also incorporated the blades. There's just a motor and another prop, and that's it. Because all the complexity is here and we 3D print, the cost for complexity in 3D printing is free. It doesn't matter how complex it is. The cost of 3D printing is just the total mass. And because we're trying to minimize the mass because we're making a flyer, it's really cheap in terms of structure. The most expensive part of this is the batteries, and I don't think we can do anything about that. Okay, another last thing we have, there's the boat, which is again another one motor boat. We've come up with there's some interesting problems with having a boat with one motor. And in terms of, and that comes into the time scale. With a flyer, the time scale is very fast relative to the time scales of what you want to control with. Here, we've got this thing that's pulsing, doing a stroke at a time, and the time scales are close. So there are some issues in how do you get the, how do you control. I've got a couple papers on that. In case you're interested, I can show you them later. All right, going to the last couple slides. If we look at these different designs, many of the times what we're trying to do is we increase the performance at the cost of computation or control. Control gets a little bit more complicated, not always, but often. The passively stable one is the kind of interesting one where we got rid of an active element. We got rid of computation entirely because we could make it passively stable instead of having it actively stable and save a large amount of cost there. So if you can get rid of things by doing things passively, that's another way to save money. All right, the last main takeaway. This is the one thing that I just came up. I just started thinking about this last night, and I was thinking, I've got this thing where things are symmetric, and that's bad. In this particular case, symmetry is bad here. And then I was looking at this guy, right, where it's moving, and this is tiny, and it's moving in Stokes flow, and the legs only just move back and forth. Normally, that will just mean it would go back and forth and not make any forward progress. There's something asymmetric here in the physics that we're trying to understand to make it actually move forward. This guy, the axes are not symmetric. They're now leaning over. This thing works because it's not symmetric. The center of rotation is off from the center of mass. This guy has the flippers that are not symmetric. They're slightly leaning forward. That's why it works. Even this thing, the manipulation, the center of mass is not in the middle as we lift it up. It works because it's offset. Basically, I was thinking, wow, the main takeaway is symmetry is bad. Which then I was thinking, no, that can't be right. You have things in nature, things are beautiful because they're symmetric. It's not exactly that symmetry is bad, but when there's an asymmetry, that's what we need to exploit for under-actuated systems in order to get things to work, and maybe that's a key thing. Anyway, so that's the last slide. Thanks to all, of course, there's tons of people involved in a work like this, and thanks to NSF and Army RCTA for support. And I'll just throw this up as a reference in case anyone needs to see papers.
Great, thanks so much, Mark. That was really fascinating. A lot of cool devices there that we could dig more deeply into. What we're going to do now is we're going to take just a few questions, and then anybody at the 4 o'clock mark here in Chicago, Evanston, will officially break, but then we'll hang around, and Mark has agreed to talk some more after that. So let's take a couple of questions now. You can put it into the chat, or you can just unmute yourself.
There is a chat question. How can you instantaneously go sideways without spending time turning to the angle first? And this is, I imagine, was for the HAMR. The key there is that the point that is turning sideways is not over the wheels. It's in front of the wheels. So if the wheels turn, because you're in front of it, it will instantaneously go sideways, that particular point.
Yeah, I think another way of thinking of that is any point off the axis of the rear wheel of the wheels, you can control that to move in any linear direction you want, right? So you choose a linear direction for that. There's a one-to-one mapping for that linear velocity to the wheel speeds. and that breaks when it's on the wheel axis. So now you know you can move that point in any linear direction you want. So the only thing left is to also be able to orient yourself at the same time.
Am I right that there is still a set of twists that can't be achieved if you were to take the coordinate system and put it on the, like if you take a twist that is a linear motion for a frame mounted over the wheels and can transform it into the space of the coordinate system on the platform, you can't do that, right? Or am I tricking myself here?
Because you're
Confusing
not
me.
on the wheels, I think you can do almost anything.
Yeah, no, I think I'm wrong. I think I'm thinking about it wrong.
Okay, other questions?
Hi, Mark. I think that. Oops.
Anna, you have a question.
Sorry about that. Thank you for the great talk. I really liked your conclusion about exploiting asymmetries in robots and robot designs. And I was wondering if you guys have thought at all about designing robots for having asymmetries, or like how you would go about planning to exploit asymmetries in design instead of like finding them and then exploiting them. They already.
That's a great question. I mean, so I literally thought of this yesterday. So I haven't tried to think about it. But it may be that intuitively or maybe what do you call it, subconsciously, when we think about, oh, we need this to happen, how can we have this happen? Well, we need this to be asymmetric, and we didn't think about it as being asymmetric, but it was like the control for Piccolissimo, having the mass be offset to get it to spin. We didn't think of it as asymmetry so much as it needs to be off in order to do a pulsing type motion.
Yeah, I think the other key piece of that, Mark, is the asymmetry and then the time multiplexing or whatever you called it, using the infinite dimensional trajectory available to you of the control plus that asymmetry is powerful.
Yeah.
Hi, Mark. Really enjoyed the talk. I do swarm robotics, so getting stuff cheap is very important. I'm just wondering, like, if you can give any pointers for your brainstorming process, right? Because a lot of this is, looking at things in a different perspective, and I'm just wondering if you can kind of walk us through.
Yeah, that's a great question, and so the one thing that I have done, not necessarily on explicitly on purpose, but one of the things we do a lot in GRASP and in my group and in other things is we have a lot of people that are not normally thinking the same way. So like artists, I have a couple classes with architects where we do performance art. They build robots and then we do things, and so they don't think the same way. We in GRASP Lab, we've started this thing where we've started to expand our faculty to include affiliated faculty, which includes nursing professors, architecture professors, sociology professors, people who are interested in using robotics, but not necessarily experts in robotics. And so having that type of things coming out from left field is often very useful for the brainstorming process in terms of coming up with different ways of doing things. But it's a super important question that is really hard to answer.
Thanks.
Any other questions? I've got several, but I'm going to stop the recording before I start asking them. So we're at the 1 hour mark. I want to thank everybody for coming. Thanks to Mark for giving us this presentation. A lot of really inventive things to think about. And I agree with Petrus, just kind of asking these questions that might not normally occur to one is refreshing to hear. So I'm going to officially end the seminar now. Anybody who would like to stick around, Mark has graciously agreed to hang around and just talk about whatever. And so thanks everybody for coming, and thanks again, Mark, for your presentation.
Thanks, Mark.
Okay, I'm going to stop the recording.